Break to thermodynamics. Today our topic is break to thermodynamics. In this topic, first of all, we will learn about what is break to thermodynamics. Break to thermodynamics is a concept that tells us about the macroscopic to microscopic properties. So in thermodynamics, we study macroscopic properties, but in case of statistical thermodynamics, we study about the microscopic properties, and for this term, we use break to thermodynamics. After this, we will also study about the why we study break to thermodynamics. We find the reason why we study break to thermodynamics, and after this, we will calculate all the properties of system from by using partition function. So, what is the partition function? We will see in the further lecture, and after this, we will also study about the conditions for thermal equilibrium, and in last we see an example and solve it. So these are the content which we study in this lecture. So watch this video from start to end, and if you have any question, leave your question in comment section below. First question which arises while studying break to thermodynamics is what is break to thermodynamics? So answer is very simple. It is a mathematical connection that helps to link the microscopic behavior of individual particle in a system to the macroscopic properties described by thermodynamics. As I already tell you that in thermodynamics we study particles on macroscopic level, but we move to statistical thermodynamics, and in which we study particles on microscopic level. So break to thermodynamics relate the microscopic properties of a system to its macroscopic behavior. Its importance to make a direct connection between the quantum state of a system and its thermodynamic properties such as free energy, the pressure and the entropy. So this is the basic introduction for break to thermodynamics, and that's why we study break to thermodynamics to relate microscopic properties of a system and macroscopic properties of a system, and in last we can calculate the thermodynamic properties of a system from a knowledge of partition function. What is partition function we see further in this lecture. So the question is, what is partition function? In simple term, partition function is a function that describes the statistical properties of a system in thermodynamic equilibrium such as temperature and volume. In further detail, if we see a partition function calculates thermodynamic properties such as heat capacity, entropies and equilibrium constant. We can calculate all these properties and see further in this lecture. For this, we have to study why we study break to thermodynamics. So answer is very simple, as I already have explained this, that it's important to make a direct connection between the quantum state of a system and its thermodynamic properties such as free energy, the pressure and entropy. And secondly, we can calculate all the thermodynamic properties of a system from a knowledge of partition function. So free energy can be calculated by using this formulation: F is equal to minus kBT natural log Q into nVT. Here n means number of particles, V volume and T temperature, where this term is the partition function of the system which we use further in this topic, and which is the integral of Boltzmann factor. Let us calculate all properties of a system from by using partition function. So let us prove this connection in the canonical ensemble. We see canonical ensemble in previous lecture very deeply. So if you did not see that lecture, go to see that lecture, and after that see this video. In the canonical ensemble, the probability of being in the quantum state psi I is the wave function. So, and this factor is given by Boltzmann. On the other hand, when the probabilities are not equal, the entropy is given by this formulation. Here S is the symbol of entropy. This is Boltzmann constant, and by using this formulation we can calculate the probabilities. In further process, we take this Z on upside and take a natural log and take negative sign between them. So we can write this formulation in another type, such as, so this was the second step in which we take natural log of z function, and minus sign shows the, because this was in division, we take an upside and take a negative sign. Further, this formulation is used to calculate or sum up all the quantum states. So this is the entropy, symbol of entropy. So the sum over quantum state is given in this equation as a part due to natural log z and a part containing EI over kBT, which is constant energy divided by Boltzmann with respect to temperature, which involves the mean or average energy. Now we will sum up all the probabilities as in this formulation. Here S is the entropy. So we rearrange all the values and use this formulation. The quantity U minus Ts is the average value of the Helmholtz free energy, which is shown by symbol F. A function of state tells us that we can relate the free energy to a partition function Zl. So Z is the partition function and U is the free energy and T is the temperature and S is the entropy. We use this formulation, get this equation. So that's the equation in which we can put energy and put values and get free energy value. So in final step we get this value because U minus Ts is equal to F, which is free energy. So free energy can be determined by this formulation. So this is equation, one of the foundation stone of statistical mechanics. So breakthrough thermodynamics helps us to find the free energy value of particle or different system of particle by using this formulation. Here F is the symbol of free energy and kBT is the natural log and kBT is the Boltzmann constant. Natural log Z means partition function. So Z is the partition function symbol and we take its natural log. Once we know all the quantum state of a system and their energy eigenvalues, we can calculate Z, which means partition function, and hence obtain the free energy of the system. So Z acts as a bridge connecting the microscopic energy state of a system to the free energy, then to all the large scale properties of a system. This was the main thing which we studied, which we discussed in the introduction, that breakthrough thermodynamics help us to study microscopic to macroscopic and macroscopic to microscopic properties. In simple thermodynamics we study macroscopic properties, but in microscopic we go to statistical thermodynamics and study on micro level. So before proceeding you should reread this section, and because it is important to the rest of the subject in the particle, you should remember these equations. So these equations can be used to find free energy and partition function. This shows the partition function and this shows the free energy. So if you want to find the free energy, then use this formulation, and if you want to find the partition function, here Z shows the partition function. This is the symbol of partition function which we use. So you can use this formulation to find partition function. Here some conditions are given for thermal equilibrium. So these conditions contain first step, that Boltzmann probability distribution occur when a system is in contact with the heat bath. For example, if a heat is transferred to environment, then this will be the heat bath for a system. The second requirement that the probability distribution satisfies is 5.1.7 equation places a several constraints on a system. So this equation is given here. We already see this formulation for partition function and already studied that kBT is the Boltzmann constant, is the energy, and Z show the function. So if the distribution is not the Boltzmann probability distribution, then the system cannot be in thermal equilibrium with the heat bath. How do we tell if this is the case? So this is the question for all of you. If you know about, if you know that if the Boltzmann probability distribution is not given, then how you can define this case? So if you know the answer, leave your answer in comment section. To explain the conditions for thermal equilibrium, we suppose that the system of n atom has a series of energy eigenvalues with the ground state having an energy. So E0 shows the ground energy, which is 0 because particle or electrons or moving particles are at rest. The system is in contact with heat bath at temperature T, so that the probability of finding it in quantum state psi I, here psi is the wave function, is given by Boltzmann probability distribution. So Boltzmann probability distribution, we use partition function. Here Z is the partition function which give us the probability distribution. So the ratio of the probability of being in the quantum state psi I to that of the being in the ground state. So in quantum state or in ground state, for ground state we use this formulation which shows the P0 and I shows the quantum state. So here is the energy and this is the Boltzmann constant. We can find the values from zero level to quantum state. So micro to macro and macro to micro can be stated, or a probability distribution can be found through this formulation. If we go further in detail, this formulation, this equation must be correct for all the quantum states. For otherwise, the distribution would not be the Boltzmann distribution. It follows that the term temperature of the heat bath can be found through this equation. So this is the equation for further formulation we use for finding the temperature, provided that the value of T is the temperature. So obtained value is the same for all states psi I, where psi is the wave function of particle. We can use equation 5.5.2. So this is the equation to calculate the temperature from the probability. So first of all we find the probability, then find the probability from ground level to quantum state, and in last we find the temperature. In last, this is the example for all of you. If you have to solve this example on your own behalf. If you did not find your answer or unable to solve this question, so ask me in comment section. I will solve it into the next video.